Hello everyone! In this video, we're going to take a look at the roll center part 5, and when there's a large lateral acceleration during a constant speed cornering, we're going to look at what the lateral load transfer elements are, and how to express the exact load transfer with these load transfer elements added. Here we have the contents of this video. This video will explain the elements of lateral load transfer, which are the rigid body roll motion, sprung mass roll angle, tire stiffness effect, and angular momentum effect among the lateral load transfer elements. Among the lateral load transfer elements, the gyroscopic precession effect caused by angular momentum in particular is not well known and difficult to understand, so this video will only give an overview, and the next video will explain in detail and with practical examples to make it easy to understand, and explain what the exact expression of lateral load transfer that combines all of these effects is. The content explained in this video is all about steady-state cornering with constant speed. In this case, the roll angle and yaw rate are constant. Cases other than steady-state cornering will be explained in a next coming up videos. Let's take a quiz. Which of the following correctly describes the lateral load transfer? 1. If there is no body roll, no load transfer occurs. 2. If there is no axle roll, no load transfer occurs. 3. Even if there is no body roll, load transfer occurs. 4. The gyroscopic effect of the wheel and the overturning moment are unrelated to load transfer. Choose one of these four. First, let's analyze the rigid body roll motion model, which is the simplest to calculate. When the lateral acceleration is small, the body roll is small, the suspension is symmetrical, and the tires are not deformed, so the entire vehicle can be considered a rigid body and the load transfer can be calculated. To obtain the load transfer of a rigid vehicle, two assumptions are made. All parts of the vehicle are rigid and do not deform, and all parts of the vehicle move as one rigid body without relative displacement. Therefore, the wheels and the body move as one, there is no tire deformation, and the relative motion of the suspension, including the spring, is all ignored. As shown in equation 1, W is the mass m times the gravitational acceleration g, and as shown in equation 2, Fy is the mass m times the lateral acceleration ay, t is the wheel track. Cg represents the center of gravity of the entire vehicle, and h represents the height of the center of gravity of the vehicle. Also, Fzl represents the left wheel vertical force, Fzr represents the right wheel vertical force, Fyl represents the left wheel lateral force, and Fyr represents the right wheel lateral force. All four forces shown here are the combined forces of the front and rear wheels, respectively. Let's calculate the load transfer for the rigid body roll motion using the physical quantities introduced above. In this video, we will only consider the case where a vehicle turns left at a constant speed on an even road without banking angle. The figure shows the rear view of a vehicle driving on a road of radius r. The total lateral force is the sum of Fyl and Fyr, which is also equal to the vehicle mass multiplied by the lateral acceleration, and the lateral acceleration is equal to the vehicle speed v squared divided by r, so it can be expressed as equation 3. On the other hand, the total weight of the vehicle must be equal to the sum of the vertical reaction forces, so it can be expressed as equation 4. If we calculate the moment at the center of gravity Cg of the vehicle, we can obtain equation 5, and by substituting Fy in equation 3 into equation 5, we can obtain equation 6. Next, by rearranging equation 7 for Fzl, we can obtain equation 7. By substituting Fzl in equation 7 into equation 6, we can obtain equation 8. Next, by rearranging equation 9 in the same way for Fzr, we can obtain equation 9. By substituting Fzr of equation 9 into equation 6 and rearranging, we can obtain equation 10. Equation 8 represents the increase in the load on the right wheel located on the outside. The first term on the right represents the original vertical load in the straight line state, and the second term represents the vertical load increased by the lateral acceleration AY during cornering. On the other hand, equation 10 represents the decrease in the load on the left wheel located on the inside. The first term on the right represents the original vertical load in the straight line state, and the second term represents the vertical load reduced by the lateral acceleration AY during cornering. Let's find out the effect of the height of the center of gravity CG and track on the rigid body roll motion. Using the previously derived equations 8 and 10, we can obtain the load transfer and the moment due to the load transfer. From equation 8 and 10, the load transfer FTL can be expressed as equation 11. From equation 11, we can see that the load transfer FTL increases as the height of the center of gravity H increases and decreases as the track T increases. Continuing from equation 11, the moment tau TL due to the load transfer FTL can be expressed as equation 12. From equation 12, we can see that the moment tau TL due to the load transfer FTL increases as the height of the center of gravity H increases. This time, let's find the safety coefficient for rollover for the rigid body roll motion model of the vehicle. When the inner wheel separates from the ground, FZL becomes 0, so the acceleration AY at this time can be found as in equation 13 from equation 10 obtained above. Since a rollover occurs when the inner wheel separates from the ground, the acceleration AY at this time is expressed as the rollover acceleration AR. If equation 13 is rearranged for the rollover acceleration AR, equation 14 can be obtained. If the acceleration corresponding to the maximum grip force that the tire can generate is a max, the safety coefficient SC for rollover can be expressed as in equation 15. What the safety coefficient SC expressed in equation 15 means is that if a max corresponding to the maximum grip force of the tire is less than the rollover acceleration AR, the vehicle rollover will not occur. In other words, because the lateral acceleration a max corresponding to the maximum grip force is reached before the lateral acceleration AY reaches the rollover lateral acceleration AR, the lateral force of the vehicle exceeds the friction limit of the tire and the vehicle slides on the road. In this case, no rollover occurs and the tires just slide on the ground. The value of the safety coefficient SC is greater than 1 for general passenger cars, but is generally less than 1 for trucks. The smaller the safety coefficient, the greater the possibility of rollover. Continuing to substitute the rollover lateral acceleration AR of equation 14 into equation 15, we can obtain the result of equation 16. As we expected, we can see that the safety coefficient increases as the track becomes wider and the height of the center of gravity becomes lower. The rollover acceleration equation derived from the rigid body roll motion model is used in most countries for regulations to prevent rollover. This regulation value is called SSF, or static stability factor. Let's find out what it is. If we organize equation 14 obtained above into the ratio of rollover acceleration to gravitational acceleration, we can obtain equation 17. The value of equation 17 is called the static stability factor and is used as a regulation value for safety regulations to prevent rollover. The SSF of SUV vehicles is in the range of 1 to 1.2, and the SSF of passenger sedans is in the range of 1.3 to 1.6. Up to now, all equations have been derived on the assumption that the entire vehicle is a rigid body. However, actual vehicles are not rigid bodies and have mechanisms that can be transformed in various ways. For example, the body can roll due to the elasticity of the spring, shock absorption is possible due to the elasticity of the tire and suspension bushing, and the suspension links constantly change their geometry. Therefore, when the lateral acceleration is relatively large, the center of gravity and track width change, so the lateral acceleration cannot be accurately expressed by equation 14. Therefore, the rollover of an actual vehicle occurs at a lateral acceleration lower than the rollover acceleration AR of the rigid body roll motion model expressed by equation 14. The ideal rigid body modeling we have looked at so far does not fit with real vehicles. When the lateral acceleration is large and the roll center is far from the center of gravity, body roll occurs, the suspension is no longer symmetrical, and the center of gravity moves slightly outward from the turning vehicle. Therefore, as the lateral acceleration increases, there are many factors to consider in load transfer. As a result, the equations for the vertical load expressed in equations 8 and 10, the load transfer amount FTL expressed in equation 11, and the moment tau TL due to the load transfer amount expressed in equation 12 are no longer accurate. Therefore, these equations must be supplemented and used to improve accuracy in cases where the lateral force is large. First, since the vehicle is not a rigid body, the sprung mass does not move integrally with the unsprung mass, but moves relative to the roll center. Therefore, let's look at what items need to be supplemented in the roll center model. When the lateral acceleration is large and the roll center is far from the center of gravity, body roll occurs, the suspension is no longer symmetrical, and the center of gravity moves outward from the turning vehicle. In addition, the right tire is compressed vertically and the left tire is expanded vertically, so the axle rolls, causing the center of gravity to move outward. In addition, the lateral deformation of the tire due to the lateral force generates an overturning moment in the tire, which increases the outward load transfer. Next, when the vehicle turns, the direction of angular momentum of all rotating parts continues to change, and this state continues throughout the turn, so a gyroscopic effect occurs, causing another overturning torque due to precession to be applied to all wheels and increases the outward load transfer. In this video, I will explain the four effects above. In addition, aerodynamics also affect the load transfer. Aerodynamics can have a significant effect. Your motion also has an effect. There is a lot to explain about aerodynamics and your motion, so I will explain it in the next coming up videos. Among them, the gyroscopic precession effect is difficult to understand intuitively because it is about angular momentum, so I will only give an overall overview, and in the next video, I will prepare a lot of materials and explain it in detail with sufficient examples. How can we obtain a load transfer equation with improved accuracy, including the load transfer elements discussed above? First, let's look at the load transfer of the sprung mass in the roll center model. If we rewrite equation 14 obtained above in terms of torque, it can be expressed as equation 18. The left side of equation 18 is the active torque generated by the lateral force due to lateral acceleration, and the right side is the reactive torque generated by the vehicle as a reaction to the active torque. The figure here shows that when the vehicle turns on a road of a constant radius at a constant speed, the lateral acceleration AR acts, and the roll angle of the sprung mass is tilted by phi s. While each phi s increases from 0, cosine phi s is an approximation of 1, but sine phi s is an approximation of phi s. In other words, when each phi s increases from 0, the lateral change in the center of gravity is much larger than the change in the height of the center of gravity. Therefore, the height h of the center of gravity can be used as is, as in equation 19. On the other hand, since sine phi s is an approximation of phi s, h phi s must be used, as shown in equation 20. Therefore, the height h from the roll center to the sprung center of gravity can be used as is, but the length h sine phi s by which the center of gravity of the vehicle has shifted laterally must be included in the calculation of the load transfer since it has a non-negligible size. Since half t, which is the length of the moment arm for the sprung weight, is reduced by h phi s due to the shift of the center of gravity, this can be expressed as equation 21. Equation 21 can be rearranged to obtain equation 22. The first term on the left side of equation 22 represents the moment of lateral acceleration acting on the center of gravity of the entire vehicle and is represented by tau c as in equation 23, and the second term of equation 22 represents the torque generated as a result of the center of gravity moving by h phi s and is represented by tau s as in equation 24. Therefore, equation 22 can be expressed as equation 25. Here, we need to take a closer look at the meaning of the newly obtained rollover acceleration equation 22 using the Roll Center model. Comparing equations 18 and 22, we can see that the msgh phi s term has been added to equation 18. msgh phi s is one of several total active torques that must be considered to obtain the accurate rollover acceleration while the vehicle is turning. Similarly, we can add additional load transfer terms to the left side of equation 22. As explained earlier, equation 22 can be simplified to equation 25. In equation 18, the torque that tilts the vehicle outward is added to the left side, and the torque that tilts the vehicle inward is added to the right side. Most of the active torque that occurs in the vehicle tilts the vehicle outward and is added to the left side. The fact that the active torque is added to the left side means that the lateral acceleration AR corresponding to the vehicle rollover is smaller. Therefore, the lateral acceleration AR calculated by equation 22 is larger than the lateral acceleration AR calculated by equation 18. What this means is that the lateral acceleration AR calculated by equation 22, which takes into account the vehicle's roll center, is less than the lateral acceleration AR calculated by equation 18, which treats the entire vehicle as a rigid body. The value of the lateral acceleration AR calculated by equation 22 is more accurate. Let's take a closer look at the meaning of equations 18 and 22 obtained earlier. If equation 18 is rearranged in terms of ARH, we can obtain equation 26. If ARH is plotted on the vertical axis and track T is plotted on the horizontal axis, equation 26 can be represented by the blue straight line in the figure. Once track T is determined, the lateral acceleration ARH that causes the rollover is determined and can be represented by the blue dot in the figure. Next, if equation 22 is rearranged in terms of ARH in the same way, we can obtain equation 27. If ARH is plotted on the vertical axis and track T is plotted on the horizontal axis, equation 27 can be represented by the green straight line in the figure. Once track T is determined, ARH that causes the rollover is determined and can be represented by the green dot in the figure. The slope of the green line in equation 27 is the same as that in equation 26, but it moves downward due to the vertical axis intercept of the second term. In equation 26, which is calculated ignoring the horizontal movement of the sprung center of gravity, the track width required to withstand the rollover lateral acceleration AR is T1. However, in equation 27, which is calculated considering the horizontal movement of the sprung center of gravity, the track width required to withstand the rollover lateral acceleration AR is found to be wider, T2. The track width delta T that must be widened can be calculated using equation 28. Meanwhile, let's fix the track width to T1 and look at the blue and red points on the vertical line passing through T1. The red point is below the blue point by delta ARH on the vertical axis. Delta ARH is the same value as the vertical axis intercept value of the green straight line represented by equation 27. Assuming that the height h of the center of gravity does not change, the rollover acceleration AR must be lower than the value AR obtained by equation 26 on the blue straight line. This fact means that the lateral acceleration AR that causes rollover is smaller because the center of gravity of the sprung mass has shifted outward. Therefore, rollover occurs at a lower lateral acceleration than the lateral acceleration value obtained from equation 26. The rollover lateral acceleration is the lateral acceleration at the instant one wheel leaves the ground, so it is directly related to the load transfer. The previously derived equation 25 additionally includes only the lateral displacement of the center of gravity of the sprung among the load transfer influence elements. We derived equation 25 to understand how to establish an equation that reflects the elements affecting the load transfer. If there are additional load transfer affecting elements to consider, you can add the load transfer factor in the form of torque on the right side of equation 25 in the same way equation 25 was established. Therefore, if you add additional load transfer factors to equation 25, it will have a form similar to equation 29. As explained earlier, in addition to the lateral displacement of the center of gravity, there are 6 torque elements affecting the load transfer on the right side. Since we have already looked at 1 and 2 of them, I will explain the remaining 2, tire overturning moment and gyroscopic precession effect. As previously announced, there is a lot to explain about the effects of aerodynamics and yaw, so I will cover them in the next video. Let's look at the overturning moment of the tire. Fy and Fz are the lateral force and vertical load for the front and rear wheels, respectively, and the total load is assumed to be evenly distributed to all wheels. The figure shows the tire of a vehicle receiving a centripetal force 1/2 Fy. In the case of a passenger car, it is assumed that all tires receive a centripetal force of the same direction and magnitude, and the direction and magnitude of the vertical force are also assumed to be the same for all tires. Let the centripetal force received by all tires be 2 Fy, and the vertical force received by all tires be 2 Fz. In addition, let's assume that the lateral stiffness of one tire is Ky, and the tire elastically deforms in the lateral direction. When the vehicle turns, the centripetal force Fy acts on the tire. The sum of the centripetal forces of all wheels is equal to the total centripetal force, and the sum of the vertical forces of all wheels is equal to the total vertical force, and if the tire elastically deforms, the centripetal force and the vertical force can be thought of as being evenly distributed to the 4 wheels as a quarter of the load. Therefore, the vertical force acting on the 2 tires, the front and rear wheels, can be expressed by equation 30, and the lateral force can be expressed by equation 31. Before the centripetal force is applied to the tire, the wheel center and the center of the tire contact surface are aligned on the vertical line, but when the centripetal force is applied, the center of the tire contact surface moves inward by the distance delta dy relative to the wheel center, so that they do not coincide on the vertical line. Accordingly, the lines of action of the forces for half the vertical reaction force Fz and half the vertical load Fz are separated by the distance delta dy. As a result, a couple moment, which is a tire overturning moment, occurs. Therefore, the overturning moment for one wheel can be expressed by using the vertical force couple Fz, as in equation 32. Meanwhile, the lateral load for one tire can be expressed by using the lateral stiffness Ky, as in equation 33. If arranging equation 33 with respect to delta dy, equation 34 can be obtained. By substituting delta dy of equation 34 into equation 32, equation 35 can be obtained. In equation 35, since the normal force Fz is 1/2 mg as shown in equation 30, and the centripetal force Fy is 1/2 mar as shown in equation 31, the overturning torque for one tire can be expressed as equation 36. Therefore, the sum of the overturning moments of the 4 tires acting on the entire vehicle can be expressed as equation 37. From now on, we will look at the gyroscopic precession effect that occurs in tires and wheels. I will explain the details and terminology of the gyroscopic precession effect in the next video, but here I will briefly explain the gyroscopic precession effect that occurs in parts that rotate about the lateral axis while the vehicle is turning. In the following explanation, the tire and wheel will be referred to as wheel. In a vehicle driving straight, the wheel has an angular momentum value that is proportional to the rotational speed and the mass moment of inertia. This angular momentum is a vector quantity that has a magnitude and direction. The figure here shows a state in which a vehicle enters a road with a certain radius while driving straight and turns to the left at a certain speed. As shown in the figure, I will explain a moment when the vehicle is located at the position vector r based on the origin. First, in the figure on the left, when the vehicle turns left on a road with a certain radius r, the direction of the vehicle constantly changes. Accordingly, the direction of all rotating parts of the vehicle also constantly changes. The direction of angular momentum can be found by applying the right-hand rule to the direction of rotation of the wheel, and is the direction of the center of rotation. If the direction of the vehicle continues to change during a left turn, the direction of angular momentum also continues to change, and in order to continue to change the direction of angular momentum, torque must be continuously and uninterruptedly supplied. This torque is supplied from the tire, and since the yaw rate occurs about the positive z-axis during a left turn, the torque axis is the positive z-axis. On the other hand, since the tip of angular momentum arrow tends to rotate toward the tip of the torque arrow, a precession movement occurs about the positive x-axis. Therefore, a wheel overturning moment is created which tends to rotate the wheel towards the outside of the vehicle. Even when making a right turn, the wheel tipping moment occurs equally toward the outside of the vehicle, just as in a left turn. This time, we will learn about the gyroscopic precession effect that occurs when a vehicle turns to the right on a road with a certain radius r. In the case of a right turn, the direction of the vehicle also changes continuously. Accordingly, the direction of all rotating parts of the vehicle also changes continuously. The direction of angular momentum can be found by applying the right-hand rule to the direction of rotation of the wheel, and it is the direction facing outward from the center of the turn. If the direction of the vehicle continues to change during a right turn, the direction of angular momentum also continues to change, and in order to continue to change the direction of angular momentum, torque must be continuously and uninterruptedly supplied. This torque is supplied from the tires, and since the yaw rate occurs about the negative z-axis during the right turn, the torque axis is the negative z-axis. On the other hand, since the tip of angular momentum arrow tends to rotate toward the tip of the torque arrow, the precession movement occurs about the negative x-axis. Therefore, a wheel overturning moment occurs that tries to turn the wheel outward from the vehicle, just like the left turn analyzed above. All rotating parts of the vehicle, such as wheels, engines, transmissions, and drive shafts, act as gyroscopes. When the vehicle turns, the gyroscopic precession effect occurs in all these rotating parts in the same way. If we apply the same analysis method for the wheels to the torque generated by all other rotating parts, we can clearly see in which direction the gyroscopic precession effect occurs. Here we have a figure of the precession effect of the left-turning and right-turning gyroscopic effect all at once. Whether the vehicle is turning left or right, the precession motion caused by direction change of vehicle generates a wheel overturning moment that tries to rotate the wheel outward. The behavior of angular momentum is extremely non-intuitive, so it is difficult to analyze. Therefore, it is important to remember the physical principles of angular momentum. First, if there is a rotating object, there must be angular momentum. Torque is needed to change the direction of angular momentum. The tip of angular momentum vector arrow tends to rotate toward the tip of the torque vector arrow, and this is called precession motion. As long as the torque that changes the angular momentum is maintained, the precession motion continues. We will learn in detail why the gyroscope causes this phenomenon in the next video, from the basics to the application, but in this video, we will first learn the basics of angular momentum. Let's look at the angular motion of a point mass. The figure here shows a force vector F acting on a point mass m at a distance r from the origin in space without gravity. In this case, the torque vector tau can be expressed as the vector product of the position vector r and the force vector F, as in equation 38. If we express this as a scalar quantity, we can express the scalar quantity of torque using the angle pi between the two vectors, as in equation 39. The order is important because if the order of the vector products is changed, the direction of the resulting vector is changed. The position vector comes first, followed by the force vector. Let's derive an equation for the angular momentum of a point mass. The linear momentum vector can be expressed as the mass times the velocity vector, as in equation 40. On the other hand, the angular momentum can be expressed as the vector product of the position vector and the linear momentum vector p, as in equation 41. As before, the order of vector multiplication is important because the direction of the resulting vector changes if the order of vector multiplication is changed. The position vector comes first and the linear momentum vector comes after. The linear momentum component px perpendicular to the position vector r can be expressed as a scalar quantity, as in equation 42. Therefore, from equations 41 and 42, using the angle phi between the position vector and the linear momentum vector, the angular momentum L of the point mass can be expressed as a scalar quantity, as in equation 43. In angular motion, we can establish a relationship between torque and angular momentum by applying Newton's second law. Since linear momentum and angular momentum have similar forms, let's first look at linear momentum, which we are familiar with. Using Newton's second law, the force for a point with mass can be expressed in terms of linear momentum as shown in equation 44. It tells us that the rate of change of linear momentum per time is force. Let's prove this. In the linear momentum equation 40 defined above, mass m is an unchanging physical quantity, so if we substitute linear momentum p of equation 40 into equation 44, we can get equation 45 by taking mass m out of the differentiation. Next, using Newton's second law, if we express torque as angular momentum that one point with mass has with respect to the reference axis, we can express it as equation 46. It tells us that the rate of change of angular momentum per time is torque. Let's prove this. If we substitute the linear moment L of equation 41 defined above into equation 46 and differentiate it with respect to time, we can obtain equation 47. The last expression in the parentheses of equation 47 represents vector product, which is the product of the same velocity vector twice. The angle between two identical vectors is 0. Since sine 0 is 0, the term which multiplies the same velocity vectors together disappears. Therefore, equation 47 can be written as equation 49. Consequently, by applying Newton's second law, force can be expressed using linear momentum p as equation 44, and torque can be expressed using angular momentum L as equation 46. As shown in these two equations, force is the derivative of linear momentum with respect to time, and torque is the derivative of angular momentum with respect to time. Let's learn about the law of conservation of angular momentum. Both linear momentum and angular momentum are physical quantities to which the law of conservation applies. The law of conservation of momentum does not depend on time. If the net external torque acting on a system is 0, the angular momentum of the system remains constant, no matter what changes take place within the system. This can be expressed as equations 50 and 51. In these equations, I represents the initial state and F represents the final state. Second, since momentum is a vector, it can be applied independently to each axis. Therefore, the law of conservation of angular momentum can be stated as follows. If the component of the net external torque on a system along a certain axis is 0, then the component of the angular momentum of the system along that axis cannot change, no matter what changes take place within the system. The law of conservation of angular momentum can be expressed as equations for each motion that moves in 3 dimensions, as equations 52 for the x-axis, 53 for the y-axis, and 54 for the z-axis. As shown in these equations, the law of conservation of angular momentum can be applied individually for each axis. So far, we have derived the angular momentum equation for a point mass, but from now on, we will derive the angular momentum equation for a rigid body made up of an infinite number of point masses. The figure on the right shows a state where a rigid body rotates at a constant angular velocity around the axis z passing through the origin O. The goal we want to calculate is to obtain the angular momentum equation about the z-axis of the rigid body when the rigid body rotates about the z-axis at an angular velocity omega. From the previously derived angular momentum L of the point mass, equation 41, in a coordinate system with the origin O as shown in the figure, the angular momentum vector Li for a point mass delta mi in the rigid body can be expressed as equation 55. The scalar amount of the angular momentum Li of the point mass about the origin O can be expressed as equation 56 using the angle theta between the position vector Ri and the linear momentum Pi. As shown in the figure, the angle theta between the position vector Ri and the linear momentum vector Pi is 90 degrees, so the value of sine theta is 1. Therefore, we can obtain the last expression of equation 56. As shown in the figure, the angular momentum Li is not in the same direction as the rotation axis z. Since what we want is the angular momentum component with respect to the rotation axis z, we need to find the z-axis momentum component Liz of the angular momentum Li. From the figure, the z-axis component of Li can be found by multiplying Li by sine phi, as shown in the first equation of equation 57. The direction of the angular momentum Liz of the point mass delta mi is in the direction of the blue arrow in the figure, which coincides with the z-axis. If we substitute Li of equation 56 into the first equation of equation 57, we can obtain the second equation of equation 57. Here, if we define the radius of rotation Ri sine phi perpendicular to the z-axis as Rih, we can obtain the last expression of equation 57. In equation 57, Rih is the component perpendicular to the z-axis of vector Ri, as shown in equation 58, and is represented by the purple vector in the figure. As shown in equation 57, the angular momentum Liz is the largest when each phi is 90 degrees, and the angular momentum Liz also becomes 0 when phi becomes 0. The velocity vector vi has the same direction as the linear momentum vector pi, and when expressed as a scalar quantity, it can be expressed as the product of the angular velocity omega and the radius of rotation Rih, as in equation 59. Meanwhile, the total angular momentum Lz of a rigid body must be equal to the sum of the angular momentum of all point masses, which are its components, so it can be expressed by the first equation in equation 60. Here, by substituting the linear velocity vi of equation 59 into equation 57 and substituting this result into the first equation in equation 60, we can obtain the second equation in equation 60. Continuing to move the angular velocity omega out of the sigma function in the second equation of equation 60, we can obtain the result of the last term of equation 60. The sigma term in equation 60 obtained above is the mass moment of inertia and is represented by I. Since the angular momentum of equation 60 is the angular momentum about the axis z, it is represented by Lz, and since the sigma term is also the mass moment of inertia about the axis z, it is represented by Iz. By substituting Iz of equation 61 into equation 60, equation 62 can be obtained. As shown in equation 61, the mass moment of inertia increases in proportion to the square of the distance Rih, which is the distance the mass is perpendicular to the rotation axis. When the mass moment of inertia in a vehicle increases, a large torque is required to change the direction of the vehicle, making it difficult to control the vehicle and reducing the agility of the vehicle. On the other hand, since it is not greatly affected by an external force, the ride quality actually improves. Now that we understand angular momentum, let's continue to learn how angular momentum is used. Let's look at some examples to understand angular momentum. Here, the black part can rotate around the z-axis without friction with respect to the ground. In the left figure, a standing person is pulling the left and right masses m as much as possible. At this time, the angular velocity is omega I, the mass moment of inertia is ii, and the angular momentum is Li, which represents the initial state. Next, a standing person in the final state maintains the state of pushing the left and right masses m outward as much as possible. At this time, the angular velocity is omega f, the mass moment of inertia is if, and the angular momentum is Lf, which represents the final state. Since the mass is far from the center, the mass moment of inertia if of the final state is greater than the mass moment of inertia, ii, of the initial state, as shown in equation 63. On the other hand, according to the law of conservation of angular momentum, as shown in equation 51, the angular momentum of the initial state and the final state must be the same regardless of time. If the angular momentum of equation 51 is expressed by the mass moment of inertia I and the angular velocity omega, it can be expressed as equation 64. As shown in equation 61, the mass moment of inertia Iz is proportional to the square of the distance from the rotation axis, so the farther the mass that makes up the system is from the rotation axis, the larger the mass moment of inertia Iz becomes. Therefore, in equation 63, since the mass moment of inertia of the final state is greater than the mass moment of inertia of the initial state, the angular velocity of the final state must be less than the angular velocity of the initial state, as shown in equation 65. This principle can be applied to the movements of athletes. As an example of how the principle of angular momentum is applied to the movements of athletes, let's analyze the movements of divers using the mass moment of inertia equation 61 and the law of conservation of angular momentum, equation 62. When a diver jumps from a springboard, he stretches his arms and legs as far as possible to distribute his body weight as far as possible, increases the mass moment of inertia, and starts a slow rotation. At this time, the mass that makes up the body is farthest from the rotation axis, so our IH in equation 61 has a maximum value, and the mass moment of inertia Iz also has a maximum value. On the other hand, the angular velocity omega in equation 62 has a minimum value. According to the law of conservation of angular momentum, equation 62 maintains a constant value. In the intermediate stage, when a fast rotation is needed, the body bends so that all the components of the body are positioned as close to the rotation axis as possible. In this way, our IH in equation 61 has a minimum value, and the mass moment of inertia Iz also has a minimum value. On the other hand, according to the law of conservation of angular momentum, equation 62 maintains a constant value, so the angular velocity omega in equation 62 has a maximum value. Accordingly, by reducing the mass moment of inertia Iz, the angular velocity omega about which the body rotates can be increased quickly. Finally, before the entry, the body is again fully extended. In this way, our IH in equation 61 will again have its maximum value, and therefore the mass moment of inertia Iz will also have its maximum value. On the other hand, since equation 62 maintains a constant value according to the law of conservation of angular momentum, the angular velocity omega in equation 62 has its minimum value again. Accordingly, by increasing the mass moment of inertia Iz to its maximum again, the angular velocity omega about which the body rotates can be slowed down. Since the speed at which the body rotates is slowed down again, the rotation speed can be slowed down and the entry can be made at a close right angle to the water surface. The principle of angular momentum is also applied in figure skating, long jump, and ballet. In this example, initially, the black bottom rigid body including a standing person is stationary and does not rotate, and the standing person on the bottom rigid body is holding the yellow rigid body that rotates frictionlessly with the angular velocity omega wi in his hand. As before, the black part can rotate around the z-axis without friction with respect to the ground. In the final state, the rotating yellow rigid body held by the standing person is lifted upside down. In this case, according to the law of conservation of angular momentum, for the entire system, the initial angular momentum and the final angular momentum must be the same in both of their magnitude and direction, as shown in equation 51. The angular momentum of the initial state can be expressed as the momentum of only the yellow rigid body, as shown in equation 66, since the rotation of the floor rigid body is 0. Also, the angular momentum of the final state can be expressed as equation 67 by adding the bottom angular momentum and the yellow wheel angular momentum. In equation 67, the mass moment of inertia IBF includes the black bottom rigid body, a standing person, and the yellow rotational rigid body. Meanwhile, the wheel angular momentum of the final state is equal in magnitude and opposite in direction, because the rotation direction is opposite to that of the initial wheel angular momentum state. Therefore, the relationship between the two can be expressed by equation 68. By substituting equation 68 into equation 67, equation 69 can be obtained. Continuing, by substituting equation 66 and 69 into equation 51, equation 70 can be obtained. Therefore, the angular velocity omega b f of the floor rigid body can be obtained as in equation 71. The table shown here is a comparison of linear and angular motion. If linear motion uses force, angular motion uses moment. Linear motion uses mass, and angular motion uses mass moment of inertia. Linear motion uses linear velocity, and angular motion uses angular velocity. Linear momentum is mass times velocity, and angular momentum is mass moment of inertia times angular velocity. The work done by linear motion can be expressed as the integral of the scalar product of force and distance, as in equation 72, and in angular motion, it can be expressed as the integral of torque times angle, as in equation 73. The units of these two are the same. In linear motion, force can be expressed as the change in linear momentum with respect to time, and in angular motion, it can be expressed as the rate of change in angular momentum with respect to time. Finally, both linear and angular momentum are physical quantities subject to the law of conservation. Let's find the answer to the quiz. Which of the following correctly describes lateral load transfer? 1. Load transfer occurs even without body roll. 2. Load transfer occurs even without axle roll. 3. Even if there is no body roll, load transfer occurs. 4. The gyroscopic effect of the wheel and the overturning moment affect load transfer. Therefore, the correct answer is 3. Load transfer occurs even without body roll. Let's summarize the content of this video. The simplest mathematical modeling for calculating lateral load transfer is to consider the entire vehicle as a rigid body. In rigid body model, the entire vehicle parts are assumed to be rigid, there is no deformation, there is no relative motion between them, and they move as one unit. The first of the two indices calculated with rigid body modeling is the safety coefficient, which is the ratio of the rollover acceleration to the acceleration corresponding to the maximum grip force that the tire can generate. If the safety factor is greater than 1, the vehicle will not roll over, and the tires will slide on the ground. The second indices is the safety stability factor, which is the ratio of the rollover acceleration to the acceleration due to gravity. This value is equal to the track divided by twice the height of the center of gravity. The higher the safety stability factor, the lower the probability of rollover. The SSF of a SUV vehicle ranges from 1 to 1.2, while the SSF of a passenger sedan ranges from 1.3 to 1.6. Non-rigid body model considers the relative displacement between vehicle parts and the deformation of the parts. First, the center of gravity movement due to the suspension is considered. When lateral acceleration occurs, the center of gravity of the sprung mass moves horizontally around the roll center, and the center of gravity movement of the sprung mass at this time means the center of gravity movement of the entire vehicle. In addition, tire deformation is considered. Due to the centripetal force that occurs when the vehicle turns, the tire road contact surface is deformed in the direction toward the center of the turn along the lateral direction relative to the wheel center. Accordingly, the vertical line passing through the wheel center and the center of the road contact does not coincide with each other, so an overturning torque occurs in the wheel that tries to turn in the outward direction. The gyroscopic precession effect of angular momentum is also considered. All rotating parts of the vehicle have angular momentum. When the direction of the angular momentum is changed, a torque is generated in the direction of the precession in the vehicle parts that have momentum. An overturning torque occurs in all vehicle parts that turn in the same direction as the wheel, trying to turn outward. Among the methods for calculating accurate rollover lateral acceleration, the rollover lateral acceleration calculated with a non-rigid model is naturally more accurate than the rollover lateral acceleration calculated with a rigid body modeling, considering all the effects such as the center of gravity movement due to the suspension mentioned above, tire deformation, and the gyroscopic precession effect of angular momentum. Therefore, the rollover that actually occurs is lower than the rollover lateral acceleration calculated with a rigid body modeling. Similarly, the safety factor and safety stability factor calculated above are also values calculated with a rigid body model, so their actual values are lower. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0071, the third part of vehicle roll center, I explained how to find the roll center for various suspension types including solid axle, trailing arm suspension, torsion beam axle. In the latest video, H0072, the fourth part of vehicle roll center, I explain how to find the roll center of a suspension using force vectors and how the height of the roll center affects the driving performance. The following video will be roll center part 6. I will explain the gyroscopic precession effect on the load transfer. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye guys.